All right, so guys, Tuesday, the last time I saw you, we looked at how to solve these nonlinear systems by graphing. But just like in Algebra 1, where we started solving two-part linear systems by graphing, we then also learned there are two algebraic methods that we can use. The same is true for these types of systems as well. And what you're going to see is that the various methods that I've taught you for solving a quadratic are going to come into play when we actually solve these systems using both substitution and then also elimination. So we're going to begin algebraically by looking at how to use substitution to solve these, and then we'll end today with elimination. Okay. Now, does anyone remember from Algebra 1 what it meant when we were using substitution to solve a system? Malachi, what did it mean?
You replace one of the variables with real numbers.
Yeah. So the idea is you isolate a variable, take that quantity, and replace it in the other equation to solve. So the same thing is true here, but I think there's some strategy that should be involved. So if you look at this system, the top one is nonlinear. That's a quadratic. The second one is linear. Looking at that, I think it's going to be much easier to isolate a variable in the second equation than in the first one, and then replace a value in the first equation with whatever that quantity is. So here's what I mean by that. What I notice is that in this system, x plus y equals 4 is just a little bit simpler than the quadratic that's the first equation. Now, you have a choice in how you want to do this, but because we're using quadratics, which means like in the first equation you have x squared and x, it's going to be much simpler for you and much more convenient in the long run if you focus on just isolating y. So what we're going to do is we're going to start this equation. We're going to isolate our y value. So x plus y equals 4. To do that, we would just subtract over the x, and we find y is equal to 4 minus x. Now I'm saying it makes more sense to isolate y because if I were to isolate x and then plug whatever that quantity is into the first equation, it would have to go in two places, whereas if you just isolate y, it's only going in once, and it's for the y value. So now we're going to take this quantity of 4 minus x, and we're going to plug it in for the y value here. So here's what that's going to look like. We're going to pull over equation number 2. So x squared plus x minus y, which is now being replaced with 4 minus x. So you can see this is the idea of substitution. We are substituting the quantity 4 minus x in for y. Now I'm intentionally adding parentheses around that because I notice it's minus y, so we're going to have to distribute that act of subtraction. So that's the next thing I would do. Distribute. So x squared plus x minus 4 plus x is equal to negative 1. At this point, what we now have is an equation solely in terms of x that is a quadratic. And at this point in chapter 3, you guys now have 5 different methods you can use to actually solve a quadratic equation. Because again, when we're solving a system, we're trying to actually find the value of x and find the value of y. So to do this, let's go ahead and combine the like terms of x and x, add over the 1 with the negative 4, so we get this in standard form. So x squared plus 2x minus 3 equals 0. And now what we're going to do is solve for x using one of our quadratic methods. Now, I'm not going to take the time to list out all the methods, but we can talk about them. So at this stage in chapter 3, we have learned how to solve a quadratic equation by graphing it and finding out where it hits that x-axis. We know how to factor, how to solve by taking roots, how to complete the square, and then finally how to use the quadratic formula. I don't know at this point if you guys have a preferred method. I have noticed just from grading your quizzes, some of you do gravitate towards the quadratic formula because it works every single time, and you know it's just the same process again and again. I personally feel that factoring can be the fastest in some scenarios. And if I look at this one, this is a quadratic with the first coefficient of 1, which means it's our shorter form of factoring. So I'm going to at least test that first to see if it works. So can we think of a factor pair of negative 3 that adds to be 2? A lot of you were like kind of mumbling it.
Negative what?
3 and negative 1, right? So this is factorable. Now it's highly likely that we could have looked at this and actually ends up not being factorable, okay? But because it is in this case, I think that's gonna be the most efficient method for solving. There's no need to do the quadratic formula because we can factor. So I'm gonna go over here, factor this quadratic. So Ben, you said factors of negative 3 with a sum of 2 were 3 and negative 1, right? And remember, this is short form factoring. We don't need to actually expand the middle term and break it down step by step. We can just therefore conclude the factors are x plus 3 and x minus 1, which is equal to 0. So we've kind of got this winding process across our paper using this idea of substitution. Now at this point we're not done, right? We need to actually set each of these equal to 0. So x plus 3 equals 0, x minus 1 equals 0, and our two solutions are actually negative 3 and positive 1. Now here's the catch. If we were in section 3.1 where we're just solving a single quadratic, we would say, okay, great, those are the x-intercepts for that graph. But that's not what we're trying to do here. We're trying to solve the system and figure out where these two quadratics actually intersect, or sorry, the quadratic and the linear function intersect in coordinate space. So does anybody have an idea, now that I know my x's, how I could finish the problem off? Isaac, what do you think? Yeah, to solve for what? Yeah, to solve for y. Now, let's shortcut where we can, right? If we're gonna plug these x's back into one of the original equations to solve for y, do you think it makes more sense to put it in equation 1 or equation 2? Yeah, 2, right? Because it's a lot simpler, it's just a linear function. So now what we're going to do, and I'll write this out for us, now we're going to plug the x values in to solve for y. And again, you could choose the first one if you really want to push yourself a little bit. I don't think any of you want to though. Some of you are shaking your head, so let's just plug it into the linear function. So if we put negative 3 into the linear equation, we have negative 3 plus y equals 4. If you add that over, we get 7. So here's one solution, the point negative 3, 7. The other one, x was equal to positive 1. We have 1 plus y equals 4. So if you subtract the 1, you get 3. And there's our second solution, the point 1, 3. And that's the idea. Of course, I always want to tie this back to Desmos, and I realize the wrestlers can't see this, but I'm still going to project it over here. I want you to understand what we just figured out. We figured out that if we were to graph these two functions in coordinate space, those are the 2 points where they're going to intersect. So equation number 1 for us was x squared plus x minus y equals negative 1. So there's our parabola. Oh, you guys can't see this. Hold on. Let me pull up Desmos. There we go. There's the parabola. And then our linear function was x plus y is equal to 4. And check it out. Solution number 1, solution number 2. 1, 3, and negative 3, 7. So that's the idea. A little bit of a longer process, but I think as you work through it, you'll find it can be pretty slick to use. So what I'd like to do now is give you one for you guys to try, remembering that all of your quadratic methods are available to you. So when you actually do the substitution and you get that one quadratic, you can choose whatever your kind of preferred approach is, but this is the one that I'd like you to try on your own. And I'm gonna pause the video, Trace, and we can reset. Okay, I think that started. Okay, so at least the two of you got to the point where you can now pivot to a quadratic method. It just might be hard to decide how you're gonna do that. Josh, what equation did you isolate and how did you isolate it?
Like, how did I start?
Yeah, which of the two equations did you start working with?
The second one.
And what did you do?
I subtracted x squared and you got y equals 2 minus x squared.
Yeah, I agree. So I would isolate y in the second equation. My preference is still to put it in standard form. That's just out of habit. So I'd probably think about it as negative x squared plus 2, but you get the same thing. And so then we're going to take equation 1, replacing our y value here with that new quantity. So you have 2x squared plus 4x, and then minus in parentheses negative x squared plus 2. and then that's still equal to -2. So look at your paper, just make sure you at least did something similar to that. You maybe, well, no, actually it should be almost exactly like that, because I still think it's easier to do the isolation with equation 2. Then we're gonna distribute subtraction inside, so we have 2x squared plus 4x plus x squared minus 2 equals -2. But then some of you saw when you add over that 2, our constant terms actually cancel on both sides. And when you combine our like terms of 2x squared and x squared, you get 3x squared plus 4x equals 0. So Josh and Malachi, that's the point you were at, and I think a couple of the rest of us also actually got to that point as well. The question is then this: what quadratic method is going to make the most sense for finishing this off? Can we take square roots here?
Maybe.
No, Satya, why can't we do square roots?
Because of 0.
No, the 0 would work. We have a b term. Remember, you can't do square roots if you have a b term, because there's both an x squared and an x, so that's off the table. I'm guessing most of us don't want to graph it, though Ben, you did kind of go for it with the graphing. I would say probably don't graph. Could we complete the square here? Yeah, but when we divide by a, what are we going to get here? 4/3. Not the most fun, right? Is this factorable? It is. In fact, it's like the factoring problem. Oh no, actually we didn't do it with this class. Does anybody see how this could be factored?
4 times 0.
What do both of these terms have in common?
X.
An x. So if we were to take out an x, look what we're gonna get. X times 3x plus 4 equals 0. And this is still that zero product property where we can then set each of these equal to 0. All that means is that one of our solutions is actually 0. So whenever you perform factorization, you get a single x by itself. That's a solution. It's saying one of the solutions is 0. Here, we're actually still going to get a fraction, just like we would if we were completing the square. So you'd have to begin by subtracting over the 4. And then when you divide by 3, we get -4/3. So kind of a pain, because when we plug that in, we're going to have to work with fractions, but it still totally works. Next, we're going to find the y values. So we're going to take turns plugging both of these x's into one of the original functions. Again, guys, I think it's going to make the most sense to use this second one, just because there's less going on in it. So it's just x squared plus y equals 2. So we'll plug x equals 0 in first. That's 0 squared plus y equals 2. So we know here y has to be 2. So that's my first point of solution, 0, 2. Then this is the less fun one. If we plug in -4/3, we'll have to take -4/3 and square it, because that's being added to y, which is equal to 2. What would -4/3 squared give us? Trace?
16/9.
Yes, your name's not Trace, but that is true. 16/9, good. So 16/9 plus y equals 2. Here's the thing though, we have to subtract 16/9 now from this whole number. This needs to have a like denominator with 16/9, right? So if you convert 2, what was it, Ben?
18/9.
Yeah, so you scale it up by a factor of 9, so it becomes 18/9. And then if you subtract the 16/9 from the 18/9, we get 2/9. So actually not too painful in the long run, but we do have a set of fractions for one of our points. And again, the whole idea, guys, is if I were to graph both of these quadratics, those are the two places they intersect. Okay, that's the concept here. All right, do we have any questions? Good to move on? Okay, I've got one more method, one final method to teach you. What I did today is I just had 2 examples of both, because I think they end up being fairly straightforward once you understand the process. Now, most of you in Algebra 1 probably ended up feeling like elimination was your preferred method, because it tends to be the fastest, because you're just eliminating a variable and going from there. You might feel that way about these as well, but honestly, I think substitution can also be pretty slick. Ben, do you see what's going to happen with this set of equations?
Subtract 9 from the bottom equation. That makes it so that 2x squared plus 2x equals -9, so then we can put that into the
Wait, subtract 9.
y. That's a y. I meant to say y.
Okay, yeah. So what he's noticing is that the way this system is set up, and remember, if you think back to chapter 1 when we did our systems with x and y and z, something had to be true for our approach to even work to begin with. X's had to be stacked, Y's had to be stacked, Z's had to be stacked, equal signs, and so on. So with a system like this, you want to make sure like terms are stacked as well. We've got the x squareds stacked, the x's, the y's, and the constants and the equal signs. So that's just step 1, making sure this actually works. Now, just like with substitution, your goal is always to get rid of y. So we're not going to get rid of x squared or x, because even if you were to eliminate x squared here, then you'd still have an equation that had both x and y, and that's not helpful. So the goal always is to, eliminate y. And what Ben was noticing is that this is actually already set up for us because our y's have opposite coefficients in this problem. So if I were to go ahead and add these two equations together, what's going to happen is that the y's cancel. Now the reason we add them instead of subtract is because the sum of opposites is always 0. So then this becomes 3x squared minus 3x is equal to -2. And if I add over that 2 to put this guy in standard form, we have 3x squared minus 3x plus 2 is equal to 0. And guess what? We're going to do the same thing we did with substitution. We're now going to solve this using any quadratic method. Again, it's kind of a pick your poison type thing. Now let's think through this. I've been kind of encouraging you guys to factor first because factoring can be pretty slick. But in this case, my A term is not 1, so it would be the longer form of factoring. That longer form, you do 3 times 2, which is 6. Can you guys think of factors of 6 that add to be -3?
3.
-3. Factors of 6. Wait, what factor pair? Okay, what we're saying here is 3 times 2 is 6, right? So if you want factors of 6 that add to be -3, the only factor pairs of 6 that could be negative are like -6 and 1, -3 and 2, -2 and 3. None of them end up working. You could kind of go in like a roundabout loop here, thinking of factor pairs, but none of them are actually going to have the correct sum that we need here. You could, yeah. So because factoring is not going to work, we know we can't take roots because b is present. We don't want a graph. That basically leaves complete the square or the quadratic formula. I think quadratic formula makes more sense because again, with the complete the square step, you always divide by a. That's going to become 2/3. It's just a little bit messy. So yes, I personally would use the quadratic formula here. So we're going to identify a is 3, b is -3, c is 2, and then x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c, and all of that sits over 2 times a. Simplifying the discriminant first within that radical, so 3 plus or minus the square root of 9 minus, well, 4 times 3 is 12, 12 times 2 is 24, so 9 minus 24 over 6. 9 minus 24 is -15, right? So we have 3 plus or minus the square root of -15 over 6. What can we do for the root of -15? I, yes, we're going to take out an I value. So 3 plus or minus I root 15 over 6. Now, some of you might have the temptation to want to divide all these things by a factor of 3, but you can't because the square root is a closed operation. So we cannot divide into the radical. Therefore, this is as simplified as we get, and that would be our final answer for this. Now, here's the catch. For every other example I've done so far, we would say the next thing we do is plug it in to find the y's, right? Well, with an imaginary value, we know that's not actually a specific location in terms of the way these two things are intersecting. In fact, if I were to graph both of these for you on Desmos, so we've got 2x squared minus 5x minus y equals -2. There's our first one. And then x squared plus 2x plus y is equal to 0. They're not touching, right? So at this point, we have enough information to conclude that there are no ordered pairs where these things actually intersect or interact in the coordinate space. And so what we therefore can state as our solution is that there is no real solution. So in Algebra 2, we take this type of answer to another level in that we have to conclude that there's not just no solution, there's no real solution. When you add in that word real, we're acknowledging technically there's an imaginary solution, but in terms of trying to find where these parabolas intersect, they don't, and so there's no real solution. Josh, do you have a question?
No, never mind.
Okay. Questions? Cool, then I've got one more for you guys to try. Right here. I gave you this time a quadratic and a linear function. I actually have set it up for you in a way that you can use elimination pretty efficiently. So go ahead and give that a shot, and we'll end our lesson today by talking about the solution. Here we go. Okay, so for this system, like I said, everything is already stacked. The y's already have opposite coefficients, so I'm at a place where I can immediately add these things together. So the y's cancel. You get 2x squared minus 4x is equal to 0. Again, this is like that other problem we can factor because those things share a value of x and actually a 2. So I take out a 2x, so we have x minus 2 equals 0, set those both equal to 0, and then we can find here that one solution for x is 0, the other is 2. Now, did anybody use a method here other than factoring? And what did you do?
I used the quadratic.
Okay, yeah, that would totally work. Did anybody complete the square? No? Okay, well, no matter what method you use, it should work. Of course, you just couldn't use square roots and you probably didn't use graphing. But then to find the corresponding y values, here if you plug 0 into the function, you end up with y is 5. So your first point is 0, 5. Here if you plug in 2, -2 plus y equals 5. Adding that over, you get 7. So your other solution here would be the point 2, 7. And there you have where these two things intersect in the coordinate space. Now, one thing I want to add, so one little caveat, okay, and this is just a real quick kind of in addition to what we've already done. It is absolutely possible that you could have a system that looks like this. That one's very normal, right? But then you could have 3x squared plus 10y is equal to 12. Boys.
Sorry, we're checking.
Oh, you're fine. In a system like this, that is not just set up to immediately eliminate y, right? What would you need to do to start?
Multiply by 10.
Yeah, multiply the top one by 10. Or if these were both negatives and you multiply the top one by 10, then you'd have to subtract the functions rather than add them. Remember, add opposites, subtract the same. So pay attention to that because I realize now
Or
that
just
you...
multiply it by -10.
Yeah, you could, and that's what I kind of taught you guys to do with the 3-part systems, is multiply by a negative factor, because then you're just adding every time. But do pay attention in your homework if it's not just set up perfectly for elimination. Understand you might have to do some scaling to actually make it work to get rid of the y. Okay, any questions? Cool, then Trace, you can end that, and then however you want to share that with the wrestlers. I don't know, I've had students in the past like turn them into YouTube links.
Yeah, I think that's what I'll do.
Okay, that's probably the easiest.
Yeah.